All right, hi folks, this is Larry Maslino. I wanted to record a video here to help you get started in the Module 8 homework. And the Module 8 homework has really two main concepts. The first concept is working out definite integrals, which really you did quite a bit of this in Module 7. So maybe this will be a little bit of a review. But then there's another topic called the trapezoid rule, which is new. And I'll talk about that in a few minutes. But why don't we do a few examples of finding these definite integrals. So here is a reminder of how to set this up. And I'm looking here at our textbook. And you'll notice here it says if you want to find a definite integral, what you do is you integrate the function. So integrate f of x, that's the starting function here. When you do that, you're going to end up with a new function that we call capital F. Then what you do is you plug in the upper bound b into that function, the capital F function, so you end up with capital F of b. Then you plug in the lower bound a, the lower bound a. That gets you capital F of a, and then you subtract the two. So you take capital F of b minus capital F of a. And remember, what that does is it gives you the area under the curve in that interval from the lower to the upper bound. So let's do a couple of quick examples here. This one says evaluate the definite integral is the integral from 0 to 5 of 6x. Well, always a good idea to get a sense of what the graph looks like and what area you're finding. Remember, a definite integral is a number. You end up with a number as your answer, and that number is the area under the curve. Well, I know this function 6x happens to graph as a straight line. That's not important that I know that. It's not critical that I know that, but let me graph it as a straight line. Actually, that's not a good straight line for 6x. 6x should be have a little bit of a larger slope like this. So let me draw 6x, maybe like this. So this is the function 6x. All right, and they want us to find the area from x equals 0 to x equals 5, which is here. All right, and we want to find this green area. By the way, I can actually do this using geometry because I can see this is really just a triangle. But let's use the definite integral process because that's what we want to practice here. So let's find this definite integral. All right, so what you want to do to get started is take the integral of this 6x. And remember, for this, we need the power rule for integration. The power rule for integration says if you're taking the integral of x to an exponent, the way you do that is you add 1 to the exponent and divide by that same expression, n plus 1. All right, also remember, when you have a constant in front, like the 6 that's multiplying, you could just copy that down with you. So I'm just going to copy 6 down. Now I'm going to take the integral of x to the 1. But according to my formula here, the integral of x to the 1 would be add 1 to the exponent. So that would be x to the 2 over 2. So this is going to be x to the 2 over 2. All right, and then I put this vertical line as a reminder that I have to still evaluate this from a lower bound of 0 to an upper bound of 5. Before I work this out, I might as well simplify because 6 divided by 2 is 3. So this is 3x squared being evaluated from 0 to 5. Okay, and this 3x squared is really the capital F function. It's the function that results from integrating the original function. So the lowercase f of x in our example was the 6x. All right, so let's do it. I'm going to plug in the upper bound now. So you plug in x equals 5 into that function. And then you remember you subtract when you plug in the lower bound. In our case, we're plugging in x equals 0 as the upper bound. So this is going to be 3 times 5 squared minus 3 times 0 squared. And this is going to be 3 times 25 minus 0. So it looks like the answer to this is 75. So this green area under the curve is 75 square units. If I had worked this out based on the area of a triangle, I would, of course, gotten the same answer. All right, let's do an example that's a little more challenging. So let me go to And by the way, folks, there's some good worked out examples here in our textbook. So please try to follow along with these examples, because notice the textbook is helping you by labeling. It's telling you the upper bound here is 2, the lower bound here is 0. It's trying to show you lowercase f of x is that x to the 4. Here's uppercase f of x is x to the 5/5 here. So there's a few worked out examples that'll be very good to follow. Here's a good example of a U substitution kind of example. We'll do an example like that in just a minute. But again, please try to work through these examples in the textbook, because the the MyMathLab homework problems are really based on these textbook problems. So the more you understand the textbook examples, the better you'll do on these homeworks. All right, so let me go. How about if we let's do an example here, because this one's a little messy because it involves a square root function. All right, well, first thing I'm going to do here is break this up to be the square root of 6 times the square root of x. So I'm taking the square root, and when you have the square root of a multiplication, you're allowed to separate it out to be separate square roots like this. Well, the reason I do this is I really want to rewrite the square root of x as x to the 1/2. So you remember, when you're using the power rule, you really want to have x to an exponent. So the square root of x is the same as x to the 1/2. All right, so let's work this out. This square root of 6, I'm just going to bring with me because that's a constant. Now I'm going to add 1 to the exponent here. This is the power rule that we just talked about. And I'm going to divide by that same expression, 1/2 plus 1. And I've got to evaluate this from 0 to 20. All right, so let me work this out. When you take 1/2 plus 1, right, 1/2 plus 1 is the same as 1/2 plus 2/2. Well, that's 3/2. So this is going to be x to the 3/2 divided by 3/2, evaluated from 0 to 24. But I remember, whenever you divide by a fraction, you're allowed to take the fraction and flip it upside down and change it to a multiplication. Whoops. And we're going to have x to the 3/2 evaluated from 0 to 24. All right, so now I'm just going to work this out. I'm going to plug in the upper bound 24 now. So it's going to be the square root of 6 times 2/3, 24 to the 3/2. So this is plugging in the upper bound x equal 24. And then you subtract when you plug in the lower bound. In our case, it's x equals 0. All right. Well, x equals 0 means this entire subtraction here in the back, this is all 0, right? So this is just 0. So I'm just going to go to my calculator and work out the square root of 6 times 2/3 times 24 to the 3/2, right? Let your calculator do this. And by the way, if you want Desmos, if you go to www.desmos.com, that's a calculator too. So you could just type this expression into Desmos if you wanted to. But I'm just going to use my handheld calculator here. And if I do that, I'm getting the answer 192. Right, you could try this yourself. And this is the area under the curve. Okay. All right, let's do another example. How about an example here? This one's a little different because it's a subtraction of 2 functions. Well, if you remember, the way you can work out this integration is to really take the integral separately of each one of these 2 quantities being subtracted. So here's what I'm going to do. I'm going to take the integral of 4x to the 4. That's going to get me, the 4 comes down with me because that's just a constant. The integral of x to the 4 is x to the 5/5. This 7 comes down with me because it's a constant in front. The integral of x to the 3 is x to the 4 over 4. And I'm going to evaluate this from 0 to 1, lower bound of 0 to an upper bound of 1. All right, so let's go ahead and do it. I'm going to plug in the upper bound first. I'm going to plug in 1 into this expression. So this is going to be 4 over 5 times 1 to the 5th minus 7 over 4, 1 to the 4th. Right here, I'm plugging in x equal 1. That's the upper bound. Then you subtract when you plug in the lower bound of 0. So this is going to be 4/5 0 to the 5th minus 7/4 0 to the 4th. But again, this back parenthesis is just 0. So I just have to work out 1 to the 5th, of course, is 1. And 1 to the 4th is 1. So I just have to work out this subtraction of fractions. Notice it says type a simplified fraction. So I know I have to keep this in fraction form. So a little bit of fraction work here. I'm going to use the common denominator of 20. So I'll multiply this first fraction by 4 over 4 because I want the denominator of 20. I'll multiply the second fraction by 5 over 5 because I want the denominator of 20. So it looks like this is going to be 16 over 20 minus 35 over 20. And if we work this out, this is going to be, what is this? Negative 19 over 20, I think. So let's check this answer. This looks a little suspicious here, but that's what we're coming up with. Let's plug this in and make sure this is the right answer. Negative 19 over 20. Yeah, works out. Now, what does it mean when an area is negative? Well, it turns out that if an area extends below the x-axis, the area is considered negative. So when you see a negative sign for these definite integrals, it's really an indication that the area you're calculating is below the x-axis. Let me give you an example. If I was calculating this area, let's say, I'll highlight it here in red. If I was calculating this area in red, this would be a positive area. But if I was calculating a graph that dips below the x-axis like this, let's say I was finding this area here, because this area is below the x-axis, it's negative. So it is possible to come up with a negative area because that's a signal to you that the area you're finding is below the x-axis. All right, so this example was just having, one expression subtract another. But for that, all you do is take the integral separately for each one of those two expressions. All right. Why don't we do an example? Let's do this one. This one is a pretty complicated one. So why don't we look at this one? And this one is a U substitution kind of problem. So here's what I'm going to do to get started. The first thing I want to do is get rid of square roots. Right? Remember, when you have the square root of a quantity, you can always write it as the quantity to the 1/2. So I'm going to take the square root that's in the denominator and write it with a exponent 1/2. All right, but I'm going to do one more step because when I go to use the power rule, I don't want the exponent down in the denominator. So let me take this expression in the denominator and move it up to the top. When I do that, remember it flips the sign of the exponent. So we're going to have 6x, x squared plus 1 to the negative 1/2. So by moving that parenthesis from the denominator up to the numerator, it changes the sign of the exponent. All right, well now this is a setup for U substitution. I'm going to let U be the quantity being raised to an exponent. So I'm going to let U equal x squared plus 1. And if you remember U substitution that we've talked about, you take the derivative du dx. Well, in our example, taking the derivative of x squared is 2x. Taking the derivative of a constant out here is 0. So du dx is just 2x. But if you remember, now we want to solve this equation for dx. So I'm going to multiply both sides by dx here. So multiplying both sides by dx here. That cancels with that. I end up with du is equal to 2x dx. Now I'm going to divide both sides by 2x. So that gets me dx is du over 2x. All right, this is what I need now to go do the u substitution. So you remember what you do is you now replace this x squared plus 1 with u. So that's going to be u to the negative 1/2. This 6x here, I'm just going to carry with me for a second because some of that's going to cancel out. And now this dx, I'm going to replace with du over 2x. All right, well, here's what happens now. I'm noticing this x cancels out with that x. This 6 cancels out with the 2 in the denominator, leaving you 3. So I'm going to have 3 times u to the negative 1/2 du. All right, well, now I can take the integral because now I've got this into a format that I wanted. The format was to try to get it to look like u, the integral of u to the n du, because now I could just use the power rule that says this is u to the n plus 1 over n plus 1. All right, so the 3 comes with me because it's a constant. It's going to be u to the negative 1/2 plus 1 over negative 1/2 plus 1. And I have to remember to evaluate this from x equals 0 to x equals square root of 15. All right, well, let's go work this out. This is going to be the integral. I'm sorry, not the integral. This is going to be, let me work out negative 1/2 plus 1. Negative 1/2 plus 1 is negative 1/2 plus 2 over 2, but that's just equal to 1/2. So this is going to be 3 u to the 1/2 over 1/2 evaluated from 0 to the square root of 15. All right, but if I divide by 1/2, I can flip that upside down and make it 3 times 2 u to the 1/2. All right, but I really don't want to leave this answer in terms of u. I want to go back to our original definition of u, which was x squared plus 1. So let me rewrite this. Maybe I'll rewrite this over here. Let me erase some of this. So I'm going to rewrite this. Of course, 3 times 2 is 6. So we have 6 u to the 1/2 valued from x equals 0 to x equals square root of 15. But I'm going to replace u with x squared plus 1. All right, now I can plug in. So now I'm going to plug in x equals square root of 15. So that's going to be 6 times the square root of 15 squared plus 1 minus 6 times 0 squared plus 1. Right back here is where we're plugging in x equals 0. All right, let's finish this up. So the square root of 15 squared is just 15. So that's 6 times 15 plus 1. And of course, 0 squared is 0. So that's just a 1. So this looks like 6 times 16 minus 6. I think that's 96 minus 6. So it looks like this final answer here is 90 if I didn't make any mistakes. So this was an example of u substitution. And the one thing you have to be careful about is the limits that we were working with were x limits. Don't plug these limits in for u. You've got to first convert u back into this expression, x squared plus 1, then you can plug in the upper and lower bound. All right, so this was a use substitution example. And again, you might recognize these examples from last module. You did many of these examples last module. Let's go to something different now, which is this idea of using the trapezoid rule. So if you remember from module 7, what we did in that module, and you did quite a bit of these examples, was you wanted to find the area under this curve. And what you do is you said, let me find the area using rectangles. So if you remember, we formed these rectangles and we found the area of these rectangles as an approximation to the area under the curve. But notice this approximation wasn't that good because these missing areas here was an error. So using rectangles has this drawback that you miss out on this area and your approximation is not that good. What if you changed the game plan and instead of using rectangles, what if you would use trapezoids? So what if you decided to create trapezoids? A trapezoid would look something like this. Notice how much better these areas would be to the true, notice how better of an approximation a trapezoid, by the way, folks, you know, is a figure that looks something like this, right? This is what a trapezoid looks like. So if I were to use a trapezoid instead of a rectangle, it would probably lead me to a much better estimate of the area under a curve because I would get a better match to the, to the curvature of the function. So there's a specific way to do this. And rather than calculating the area of each trapezoid, which you can do, there's a little shortcut formula because someone has figured this out for you. Rather than finding the area of each trapezoid individually, we can use a formula. So let me show that to you in the textbook. Let me come here to the text and let me go over to section 25.5. All right, here it is. So what this is saying to you is if you want to get an estimate of this area under the curve, so we're trying to find this approximate area under the curve, we're going to form these different trapezoids. I don't know if you could see them. It's a little hard to see, but this trapezoid, first trapezoid looks like this. The second trapezoid kind of looks like this. It's these blue trapezoids under the curve. All right, well, here's the formula to use. All right, so the way this works is if you want to use the trapezoid, what you have to do is find h. So here it is, h over 2. Well, h is the width of each trapezoid. There's an easy way to figure that out. I'll show you that in a second. Then what you have to do is you have to find the y value at each one of the endpoints. So if you notice in this diagram, here is an endpoint. Here is another endpoint. Here's another endpoint. Here's another endpoint. Here's another endpoint. You find the y value of each one of these endpoints. We're going to call this y sub 0. We're going to call this y sub 1, y sub 2. The way you can find these y values is you take the x value and plug it into the function. For example, if this was x equal 3 here, to find y sub 0, I would just work out f of 3. And then you plug into this formula. And I'm going to show you a worked out example. So this might be a little confusing until we see a worked out example. But here's the tricky part of this formula. Notice the first y value is just written as y sub 0. Notice the last y value is just written as y sub n. but all of these other y values are multiplied by 2. So the first y value is left alone. The last y value is left alone, but all the y values in between get multiplied by 2. You might say, why did they get multiplied by 2? Well, if you were to find the area of each trapezoid, that's what they're doing here. They're finding the area of each trapezoid. You'll see what ends up happening is that y, the interior y's, like y sub 1, y sub 2, and so on, will end up getting added together twice, which is why you see that multiplier by 2. Okay? All right, so anyway, let's do an example here to see the setup. So let's come here to a MyMathLab example. All right, and always a good idea to draw a diagram for these kinds of problems so you can get a sense of what the trapezoids look like and what the endpoints look like. All right, so here's what they're giving me. They're giving me the function is 6x squared. So that might look something like this. And they're telling me to go from 0 to 4. Okay, and they want me to use n equal 4. N equal 4 means use 4 trapezoids. All right, so let me draw 4 trapezoids. Here they are. I'll call this trapezoid A, B, C, D. All right, I need to know the width of each trapezoid. Well, we call that H. So H is the width of each trapezoid. Well, there's an easy way to calculate that. What you do is you take the upper bound minus the lower bound and divide by the number of trapezoids. In our example, the upper bound was 4, the lower bound was 0, and we said to use n equal 4. So this is 1. So the width of each rectangle is 1 here. So I can write this as x equal 1, x equal 2, x equal 3, and x equal 4. All right, well, let me label also these y values that they're talking about. Here is y sub 0. Here is y sub 1, y sub 2, y sub 3, and y sub 4. All right, and I know this function is 6x squared. Right, this curve is 6x squared. So let me figure out these y values. The x value, let me write down the x value here. So the x value is 0, 1, 2, 3, 4. Let me figure out the corresponding y value, which is 6x squared. So this is going to be 6 times 0 squared, which is 0. This is going to be 6 times 1 squared, which is 6. Then 6 times 2 squared, which is 24. 6 times 3 squared, which is 54. And 6 times 4 squared, which is 16 times 6, 96. Okay. And let me label these according to our trapezoid formula. So let me write down the formula again. Let me erase this maybe. Actually, why don't I copy this formula here? That'll probably be the easiest. Actually, let me write it out. So I'm going to erase this stuff here. All right, so we're ready to find the area using trapezoids. And in fact, why don't I label this? This would be, let's label these using the y notation. This would be y sub 0, y sub 1, y sub 2, y sub 3, y sub 4. All right, so we just figured out this is 0 here. This is 6. This is 24. This is 54. And this was 96. Okay, those are the heights of those green dots. All right, so here it is. The area is h over 2. And then I have to take y sub 0 plus 2y sub 1. Remember, these interior y's get multiplied by 2, plus 2y sub 2, plus 2y sub 3. But then this last y sub 4, does not get multiplied by 2. Let me click back here on this formula to show that to you. Notice this y here does not get multiplied by 2. The first y doesn't get multiplied by 2. The last y doesn't get multiplied by 2. But all the other y's do get multiplied by 2. All right, I'm ready to plug in then. We have everything we need. RH, you remember RH was b minus a over n. That was 4 minus 0 over 4. So RH was 1. So this is 1/2. Our y0 was 0. Y1 was 6. Y2 was 24. Y3 was 54. And remember, the last y does not get multiplied by 2. So this is a job for my calculator. 0 plus 12 plus 48 plus 108 plus 96. And if I work this out on my calculator, this is going to be 1/2 times 264, which turns out to be 132. So the trapezoid rule is telling me that this area is 132 square units. Remember, that's an approximation because we use trapezoids here to create these approximate areas. Let me draw one of the trapezoids just so you can see it. I'm going to exaggerate it a little bit. So the trapezoid is this green area, and it's slightly less than the exact area under the curve. So I'm thinking that our estimate of 132 is slightly less than the actual area under the curve. Okay. So let's see if this is right. Let's enter 132 here and see if this is, by the way, that's why they use this approximation sign here. They're trying to tell you this is the approximate answer for this definite integral. Okay. Then it wants me to find the exact value. Well, you can find the exact value using a definite integral. I'm going to let you work that one out based on the examples we've already done. Okay, folks, one thing you might notice is this is a nice place to use Excel if you want to help automate this, because you're essentially doing very similar calculations over and over. So why don't we do that? Let me do one more example of the trapezoid rule. And let me set this up. Let me use Excel just as an assistant. Of course, you don't have to use Excel if you don't want. You can set up a table like I just did on paper and pencil. But let's do, why don't we do an example like this? All right, and I've already started to set it up in Excel to save a little bit of time. All right, so here is an example. And let's do this using Excel. All right, so here it is. N equals 8 in my example, right? I'm looking at this example. Our function here is the square root of 25 minus x squared. Okay, the lower bound is 0, the upper bound is 5. Okay, and let's go ahead and draw a little diagram here, because that's always a good idea. So here is the function. I don't know exactly what this looks like. I'm just going to kind of guess it does something like that, let's say. And they want me to go from x equals 0 to x equals 5. But they want me to use 8 trapezoids. So I need to know what is the width of each trapezoid. So I'm going to be dividing these up into 8 trapezoids. Like this. Here they are. All right, here are the 8 trapezoids. I want to know what is the width of each one of these trapezoids, because that's called h. Well, to find h, what you do is you take the upper bound minus the lower bound, and divide by the number of trapezoids. In our example, the upper bound is 5, the lower bound is 0. We're dividing by 8 trapezoids, so this works out to be 0.625. Okay, and again, as you start to get into messy numbers like this, Excel is a good tool to make the calculations efficient. All right, so why don't we mark these y values? Let's call this y sub 0. This will be y sub 1, y sub 2, y sub 3, and so on. All right, so let me write out the endpoints. So first of all, let's calculate h. We already did it, but I'll just do it here in Excel. It would be 5 minus 0 divided by 8. So it's 0.625. So let's do the endpoints. Well, the endpoint is going to be 0 to begin with. Then for this endpoint, I'm going to take the old endpoint and add 0.625. And I'm going to do this. I can actually copy this down. And I need 8 rectangles, which means we really have 9 endpoints. Okay, here they are. So these are the endpoints. All right, now let's evaluate y at those endpoints. So I'm going to come here and type in a formula that says, I want to take the square root of 25 minus the x value, but the x value is this endpoint here in column A, and I have to square that like that. So I'm just going to use Excel to calculate these y values for me. I could just copy this down. So Excel has calculated these y values for me. All right, now I have to remember the formula. The formula says that the first y value stays as is. So I'm just going to copy it. Let's say equals this guy. And the last y value stays as is. But all of these other intermediate y values have to get multiplied by 2. So what I'm going to do here in Excel is I'm going to say equals 2 times this y value. And I'm going to copy these down. All right. So what I have here is I have the sum. This is representing this parenthesis right here. Okay. So let me add up those numbers. So I'm going to say here equals sum of these numbers. Okay. But if I want to find the area, I've got to take h divided by 2. So I'm going to take h divided by 2 times that parenthesis, which is that number. Here is my estimate for the area under the curve. So this is my final answer for the area under the curve. And they want me to round this to 2 decimal places. So my final answer would be 18.55. Okay, so again, I'm using this trapezoid rule. I'm using Excel to kind of speed up the calculations. But if you don't want to use Excel and you want to do this on your calculator or just using paper and pencil, of course you can do that. The idea is you find the width of each trapezoid. That's h. So remember, h is the width of each trapezoid. You can calculate h using this formula. Then you have to find all of these y values. To find the y values, you just take these x values and plug them into the function. Once you have all those answers, the trapezoid rule says you leave the first y value alone and leave the last y value alone, but all the other y values get multiplied by 2. Add all of those results together. That's this parenthesis here. Multiply by h over 2. That's your answer for the trapezoid group. All right, folks, give this a try. Let me know if you have any questions. And I'm also going to put together another short video on the discussion board for Module 8. So please look for that video as well. All right, thanks, folks.